Hello everyone, my name is Vipra Joshi and I am an assistant professor in St. Andrews Institute of Technology and Management in Electrical Engineering Department. Today I am going to deliver a lecture on subject of control system engineering. In this video, I will be explaining Introduction to State Space Analysis. This is Unit 4th topic of 6th semester in Electrical Engineering branch. State space analysis, useful technique to analyze and design of the system. We can say we used this technique for designing a system and other than analyze the system. Okay, so it can be apply on linear system, on non-linear system, time variant system, time invariant system, and SISO and MIMO means single input single output, and MIMO means multiple input and multiple output system. Okay, so we can say this technique apply for any type of system. Now this system is represented by a mathematical model. You can see here a plant and mathematical model differential equation. It has two types. One is frequency domain technique and second is time domain technique. Okay, so a system is represented by the mathematical model and it has two approach. Okay, one is modern approach and second is conventional approach. So conventional approach is also called the frequency domain approach. Okay, and the time domain approach is the modern approach and this is the conventional approach. Okay, so here we have a two type of approach. First is frequency domain approach and conventional approach. So this approach is based on the transfer function and we can apply this technique only on linear time invariant SISO system, means single input single output, and linear time invariant. So we can say it used only on LIT and SISO system, LTI and SISO system. So and this technique used is Laplace transform for their calculations. Okay, so the second technique is modern approach technique, which is based on the input and output and state variable. Okay, so we can apply for any type of system of this technique. Okay, and we can apply this technique to all systems. Okay, and we used in this jet transform. So we can say here in frequency domain we use Laplace transform and in time domain we use jet transform. This technique only apply on the LTI and SISO system and this technique apply all the type of system and it consists input output and variable. Okay, now what state space, why state space model? Okay, the state space model represent a physical system of nth first order differential equation. This form are better suited for the computer simulation than the nth order input output differential equation. Here we have some parameter, like first what is state in state space analysis. Okay, so here it refers to the smallest set of variable whose knowledge at t equal to t0 together with the knowledge of input for t greater than equal to t0, and it gives the complete knowledge of the behavior of the system at any time t greater than and equal to t0. It means we have here a present time. Suppose we have here a present time t and a initial time t0 and a final time tf. So we have here the three type of time t, t0 and tf. So it is the set of variable, we can say state is the set of variable. Okay, so it defines that how the system is going behave for any time. We conclude all the time how much and how the system is behave for any time t, t0 and tf. And second is state variable and state space in state space analysis. Okay, it refers to the smallest set of variable which help us to determine the state of the dynamic system. State variable are defined by x1t, x2t and so on xnt. And next is state vector. Suppose there is a recruitment of an state variable in order to describe the complete behavior of the system, then these n state variable are considered to be a component of the vector x3. Such vector known as state vector. It means here it is a vector of state variable. Here we denote it is xt equal to x1t into x2t and so on xn t. Okay, it means vector is represented in a matrix algebra form. So we have a vector having n component for the state analysis. Okay, now the next is state space. It refers to the n-dimensional space which has x1 axis, x2 axis and xn axis. It means x1, x2 till xn are the state variable. We know that. Okay, so now for each state variable we have an axis, and when we combine these axes for each state variable we have a axis, different type of axis, and then when we combine these axes then we can get a compute and we can get a complete n-dimensional space, and this space is known as state space. So we can say for every state variable, at first we know that what is a state variable, which gives the knowledge and which gives the which gives us the knowledge that how the system is going to behave for any type of system. These are the variable of state variable. So for each state variable we have here a space, a axis. Okay, and when we combine all the axes it gives us a complete n-dimensional space. Now find the transfer function for the state space model. Okay, so we know that state space model for linear time invariant system is x dash ax plus bu equal to y. Here it is the input equation and this is the output equation, y equal to cx plus du. Okay, here a b c d are the matrix. Now we take the Laplace transform on the both side of the state equation. So here the Laplace transform of x naught is s into xs, okay, and Laplace transform of x is xs and u is us. Here ab are the constant value, it is the matrix value, okay. And now we can take common x xs. So when we take common xs, it is s minus a, and here we can write it si minus a, because here I is the identity matrix. So here we multiply it by identity matrix. Identity matrix means 1 0 0 1. So whenever we apply any terms by the identity matrix, it gives the same result. It gives the same s, okay. So there is a no effect of identity matrix, okay, if we multiply it. Now we can write it here, si minus a into xs equal to b into us. Now here if we find the value of xs, it is si minus a inverse into b into us, okay. So this is our input equation Laplace transform, and here we find by this xs. And now output equation, we know that here the output equation is y equal to cx plus du. So we at first we take the Laplace transform of this, okay. So it is ys equal to c into xs plus d into us. Now we substitute the value of xs in the place of xs. Here we have a value of xs, it is si minus a inverse into b into us. Now when we put this value here, okay, so here then we can get the value of ys over us, it is the transfer function, okay. So it is c into si minus a inverse into b plus d. So in the above equation represented the transfer function of any system. So we can calculate the transfer function of the system by using this formula for the system of state space model. Now here if d equal to 0, then the formula become ys over us equal to c si minus a inverse into b. Here ys upon us means output upon input ratio. So this is the transfer function. Now for example, let's we calculate the transfer function of the system which represented by the state space model. Here we have a space model, we know that x naught ax plus bu. So it is the x naught, x1 naught and x2 naught. Here a is this ax into b. The b matrix value is 1 0 and u is the input. So here x equal to x1 and x2, these are on the matrix form, and here y equal to cx plus dx du, okay. So here the value of d equal to 0, okay. So now at first we write the matrix value. A value is -1 -1 1 and 0, and b value is 1 over 0, and c value is 0 1, and d value is 0, because here no element for the value for d, okay. Now the formula is become ys over us equal to c into si. Now the substitute all the value ABC matrix in this equation, okay. So we have here this, okay. So we have here si minus a. So we know that I is identity matrix, it means it is 1 0 0 1. So here we have s0 0 s. So we can calculate the si minus a, okay. It is si and minus a. Here the a matrix value is -1 1 -1 and 0. So when we subtracting both matrix, we can get here S. Okay, so we can get here S minus 1, it is S plus 1, and 0 minus 1, it is 1, and here 0 minus 1, it is minus 1, and 0 minus S minus 0, it is S. So by this we can get Si minus A. So here we have here Si minus A inverse. Okay, now we calculate the value of this. We know that the formula for the inverse value is adjoint of Si minus A over modulus of Si minus A. Okay, so you know very well how we get modulus of any matrix. If suppose we have a matrix A, B, C, D, and when we calculate the determinant for this matrix, it is A T minus B C. Okay, so by this we can get here the denominator value. It is the modulus of this Si minus A. Okay, now adjoints of A means here, so at first we calculate the adjoints of A. So if we have A, B, C, D, 2 into 2 matrix, then we calculate the adjoint. It is DA, and here at BC we have a minus sign. So by this we can get this matrix. Here S is here and S plus 1 is here, and here the sign is changed. Okay, so this is the formula for the adjoint matrix of 2 into 2 matrix. Okay, now we have to calculate this. It is 1 over S square plus S plus 1. Therefore, the transfer function of the system is given by Ys over Us equal to 1 over S square plus S plus 1. Now, state transient matrix and its property. If the system is having initial condition, then it will produce an output. Since this output is present even in the absence of input, if the output is present even in the absence of the input, we can say, and it is called the zero input response. So mathematically we can write this: x at 0 input response is e to the power 80 into x0, and here the value of Laplace transform is, we know, Si minus A inverse into x0. So here we represented phi t transient matrix by e to the power 80, and it is the Laplace transform of Si minus A inverse. So the zero input response can be obtained by the multiply of transient matrix phi t with the initial condition. So the properties for this matrix is, if t equal to 0, then state transient matrix will be equal to the identity matrix. Okay, and for the next, inverse of the state transient matrix will be the same as the state matrix we can obtain by t, replacing t by minus of t. So both values are same. So we can represent it, inverse transient matrix is phi into minus t. Now if we have t equal to t1 plus t2, then we can get matrix phi t1 into phi t2. So these are the properties for the transient matrix. Now what is controllability? Okay, a system is said to be controllable if the initial state of control system are transferred to some other desired state by the controlled input to the finite duration of time. Here this is we can get by the Kalam test. So the Kalam test is write the matrix QC in the following form: QC equal to B into AB, A square B, A n minus 1 into B. We have this type of form for the n value. Okay, here n is the order of the system. Okay, so find the QC. If it is not equal to 0, then we can say that the system is controllable. Now for example, if we have this system, okay, now by comparing we can get here the value of A, B, C, D. Here the value of D is 0, so here we have a 2 into 2 matrix, so n equal to 2. Okay, so now we want to calculate the system is controllable or not. So for this we have a formula. Here n equal to 2, it means here we have formula is, first is n equal to 0, okay, n equal to 1 and n equal to 2. Okay, so we have a formula here, B into AB. Okay, so when we at first for calculating this, we have to calculate the value of AB. Okay, so here the AB value is -1 and 1. It is nothing, it is the multiplication of the A matrix by the B matrix. Here multiplication of A matrix by the B matrix, and by we can get by this AB equal to -1 and 1. Now QC is B into AB. So here we place the value of B value is 1 0. So we have here 1 0, then -1 and 1. And if you calculate the determinant of QC, it is 1, and we can say it is not equal to 0. So this system is controllable because QC is not equal to 0. So by this we can calculate the system is controllable or not. Thank you.